Hi everybody, this is Mrs. Ellsworth, and in this video we'll be talking about Newton's 3 laws of motion, and we'll be talking about momentum. And in the 3 laws of motion, not everything is always cut and dried like it's appearing here, but we will try our best to help us understand which law we're talking about in certain situations. So let's get started. Okay, in Newton's first law of motion, if you read that, it says, according to Newton's first law of motion, the state of an object does not change as long as the net force acting on the object is 0. Okay, and I just want you to know that this is cumbersome for words from our book. So I actually have something that I like writing it as better. I like to say that this is an object at rest will stay at rest, and an object in motion will stay in motion. Okay, again, that's an object at rest will stay at rest, an object in motion will stay in motion. So if an object is resting, it's not going to move unless a force is acting upon it. And also another object that's in motion, like a hockey puck going across the ice, is going to stay in motion, except for that little bit of friction will slow it down, unless you also, smack it with a hockey stick and that's another force applied to it. So again, in my own words, this one would be an object in motion will stay in motion, an object at rest will stay at rest. Now, I just want you to know that that's kind of describing another term too, inertia. That's an object, it has a tendency to stay in the same exact motion as that. So it doesn't want to resist any kind of change of motion. So that's really kind of talking about the same thing. An object at rest will stay at rest. An object in motion will stay in motion. So I also call this one, aka means also known as, the inertia law. Helps me remember each one when I'm talking about them. Okay, and here's that object at rest. This fat cat is not getting up unless there's a force acting upon it. And then this guy who's on the slippery slide, he's going to keep on going until a force acts upon him. So he's an object in motion, is going to stay in motion. Okay, Newton's second law of motion, it is okay, this is acceleration of an object is equal to the net force acting upon it divided by the object's mass. I like to think of this this one, it has a certain formula. This means force equals mass times acceleration. Okay, and in this case right here, the force, okay, is measured in newtons. Okay, and mass is measured in kilograms. And acceleration is measured in meters per second squared. And so when we talk about this, when force equals the mass times acceleration, think about that. If you've got a really massive object, you're going to have to apply a huge force to it to get it going. So to get it to accelerate. If it is a much smaller object, it has much less mass, you don't have to need as much force to get it to accelerate as much. So there's definitely a relationship between these ones. And I just know that there's a relationship to force, mass, and acceleration. And I might even say that in my own words that there's a relationship between force, mass, and acceleration. But also, let's take a moment here to realize something else too. That newtons equals a 1 kilogram mass being accelerated 1 meter per second squared. In fact, that's a definition of a newton. So that's kind of cool because this formula shows you exactly what a newton equals. A 1 kilogram mass accelerated 1 meter per second squared. Just a little bit of extra fun info for you there. For me to help me remember these different motions, I call this one also known as F equals ma. And that just helps me remember them for when I need to come up with what the law is that I'm looking for specifically. Like when we do charades in class tomorrow, it helps us remember which one is. I like this diagram here. I've kept this one for a long time now because this man's face and his body, it just shows how he's exerting such a huge force to go and pull this semi-truck. So it just is a great way to show that it's just a great way to show that it's takes so much force to pull a large object. Okay, there we go. And next, Newton's third law. This was pretty interesting because in Newton's third law, we've heard of this one even in commercials. Okay, whenever an object exerts a force on a second object, exerts an equal but opposite force on the first object. I know this one as an action-reaction one. Okay, and the action-reaction, so this is saying that if I would go and put this in my own words, which I should have had written right here, that for every action force, there's an equal but opposite reaction force. So maybe you should add that to yours too, because that makes sense. For every action force, there's an equal but opposite reaction force. So if you think of yourself like you are on a lake here in Minnesota, and you're getting ready to jump off a boat, okay, you push back on that boat, and then you move forward. And so the boat goes backwards, and you go forward. Hopefully you do it well enough so that it doesn't hit your shins really bad, so it doesn't hurt too much, because I think we've all experienced that before. Anyways, Newton's third law is that for every action force, there's an equal but opposite reaction force. And so let me show an example of that. Oh, and I call this one, it's also known as the action-reaction force. So I like to think of this one because it, you know, if you talk about a cannon has to be on wheels or else it'll break. It's got that reaction to that bullet flying out of it, and so you get the recoil on the gun, and so it's a really good way of showing that the action and the reaction of it. And a cannon would be the same exact way. Okay, let's talk a little bit about momentum. Okay, now momentum, here is our formula. So momentum is shown with a P, okay, and it equals mass times velocity. Okay, again, momentum equals mass times velocity. So the more massive your object is, okay, the more momentum it has. The more faster that your object is going, the more momentum that it is. So if you can think of some different types of situations, like this bus right here. Okay, this bus has a very large momentum because it's so massive. Okay, if it's going fast, it's also it's massive and it's going a very high velocity, so you have an incredibly huge momentum. Compare that to a bicycle. Okay, a bicycle is not very massive. Okay, let's say it's going the same speed as the bus, but it's still going to have much less momentum than the bus. Now the whole thing is just think about that as you cross the street sometimes, because sometimes you think, oh, well, it's the law for them to stop for me. But think about it. If it is a huge, massive vehicle, it may not be able to stop because it's got too much momentum. Okay, if it's something as small as a bicycle, then it has much less momentum. So think about that. Think about your physics as you try to cross the street sometime. Okay, now momentum also we can show with elastic reactions. So the momentum of the cue ball goes into the second ball, and sometimes after this reaction occurs, after it hits, then it moves on. And sometimes after the collision, this one actually sits still because all of that energy transfers from one to the other. We call that an elastic reaction, but it's showing how the momentum will transfer from one ball to the other ball. Okay, and that's pretty much it for this whole chapter. Oh, wait a minute, I forgot about this. The momentum of that fist, okay, actually reacts on this poor guy here, doesn't it? Okay, you could also say that he had a lot of inertia. He was sitting still because he's massive, and it took a big force to change his motion. Okay, so there's quite a few forces going on here, and I can think of some different scenarios how you would think of the 3 different laws for this one. But I'm seeing an action and reaction. I'm also seeing inertia, and I'm also thinking about the type of forces behind this thing. Force equals mass times acceleration. Okay, he puts a lot of force into this to get something to accelerate this poor guy's head. Anyway, I will see you tomorrow.